Hey class, now that I did this problem, and I'll put this at the front of the video so you will see it first, but it looks like I wrote this down wrong. This is actually conservation of energy problem, so it's from chapter 7 of your book, and it's from chapter 8 of the university physics here. And of course, when you see the start of this video, you'll see that I wrote it down. I was off by one and said it all wrong. But the solution is all good. All right. So here we go. Let's go through the solution. All right, students, let me try. Really a tough one. It's from the harder book, the university physics book. It's a conservation of energy, so that's chapter 9 in the university physics. But I'm going to call it chapter 8 because it's in our chapter, in our main book, the college physics, chapter 8. Conservation of energy is chapter 8. So it's number 72, and it really says this, that a body of mass m and of negligible size starts from rest and slides down a frictionless solid sphere of radius capital R, see below. Prove that it will leave the sphere when this angle is true. Okay, so here's the angle. So if I understand the physical problem, it's going to slide, and of course I can see as it slides down, two things are happening. It seems to be going faster, and in addition, the slope gets greater, and so eventually it's just going to separate and follow the path of a parabola. And so where is that angle? And apparently they say that angle is the inverse cosine of 2/3. And I'm just kind of curious what that number would be. And so inverse cosine of 2/3 is about 48.2 degrees. So at 48.2 degrees, which I think in my picture that'd be a little bit more because 45 is kind of bisecting right here. So picture doesn't do it justice, but I think you get the idea here. So I guess I'm going to start with this principle of conservation of energy. So let me start there. The initial energy is equal to the final. And as we've said, the energies would be the kinetic energy plus the two potential energies plus any non-conservative work, so that'd be like friction or anything else like tied to it, a rope or something, equals then the kinetic energy after, I should have put an initial, and then the potential energy final. Okay, so if I come back over here and choose a grid, maybe right here at the origin, seems like a good place to measure things. Let me go ahead and start filling this out. And so its starting point up at the top, I would say it has 0 kinetic energy. And at this point in the book, we haven't done rotations, but we have lectured on it here. So I would say there's 2 kinetic energies, a transverse and a rotation. But either way, they're both 0. In fact, rotation is not even part of this one. That's why they have a block here. It might be kind of fun to do a rolling sphere next to see how that might be a little different angle and see how it might affect things. But not necessarily worrying about that. Let's go ahead and then say, well, the initial gravitational potential would be mg times its initial height. And if you are measuring from the center of the sphere, its initial height would be radius r. Maybe for completeness, I'll put the other potential energy, which is that 1/2 kx squared, the energy of a spring, but we don't have any springs in this problem, so probably shouldn't even waste our time thinking about it. But I wanted to kind of illustrate to you guys that I am thinking about it, and it's just 0. And of course, the work done by our non-conservative force, since they use the phrase frictionless, would be 0. Simply put, the starting point has only one type of energy, gravitational potential energy, and it's at a height r. So that's the left-hand side of the equation. That's the energy we start with. Now, as it slides down, it is now going to be moving. So someplace at some angle theta, it has picked up a speed and has now kinetic energy. Notice then also it is a bit lower. And so maybe I'll make a little triangle out of it. And the fact that it went down means it lost gravitational potential energy. And that makes sense because it gained kinetic energy. And so this would be mg, and maybe I'll just put up here y final. But I can look at this picture and see that y final would be this height, which this distance would be r, and so this height is adjacent to the angle cosine. So if I go r cosine theta, that would be the final height when it somewhere over here leaves the sphere. So I'm going to write here r cosine theta. And so maybe I'll put a little box around this. I suppose I could cancel an m, but let me just hold off on that. This is the information I get from conservation of energy, and it ties in the angle and the speed and the radius. Now, of course, the other thing that pops into my mind takes us back to chapter 6, where we were looking at things that go in a circle. Or was it 7? No, that must have been 6. Yeah. Wait. Well, I guess it doesn't matter which one it is. But let me continue on. But I did learn this earlier on, and hopefully you did too, that if something's going in a circle, and in this case it's, somewhere right about there, that means it's changing directions, and it would have an acceleration of v squared over r. And that's the important piece. And I will also say towards the center of the circle. So, in other words, if I go back to our free body diagram, and maybe I look at the box right here, and if I stick to something that I said back in chapter 6, or even way back to chapter 4, that usually these problems involving forces and acceleration are easier to calculate if you set your axis, one of your axes, again, it doesn't matter if it's plus or minus x or plus or minus y, but one of your axes towards the direction of the acceleration, which in this case I would say towards the center of the circle. So let me do maybe a different color. How about black here? And just say that I'm going to look at forces with my axis here. And so that's a little different than our energy axis. And so I just want to say I'm kind of doing a separate calculation, and so a separate axis. Because it was nice using this axis when I was doing energy. But it's also nice to have an axis towards the center of the circle, which back here at the beginning, that would have been this one. But now that it's moved down at some angle, it would be directed in at some angle. So in other words, the free body diagram would look something like this. We would have gravity pulling down and the normal force pulling off to the side. And then notice straight down the normal force is the center of the circle. And so coming back here and drawing a line straight down for mg, you'll see if this is angle theta, so is this. These are alternate interior angles. See, these are two parallel lines cut by a transect. And so these angles from geometry are alternate and interior and must be equal to each other. So I can put that right here. That's the main thing I want to do. Because the grid I'm using, which I will draw in black again, except not on this picture, but this picture, I want to use a grid that looks like this. And maybe I'll just call with the normal the y direction and then down the slope the x direction. So that means my axis that's pointing towards the center of the circle is the negative y axis. So when I write out the sum of the forces in the y direction and set it equal to mass times acceleration in the y direction, I can say that the acceleration in the y direction is v squared over r and towards the center of the circle. The center of the circle being the negative y direction. So that's what the forces in the y direction have to equal. Let me kind of group this together and call it negative mv squared over r. Okay, so then the other side of the equation is the sum of the forces. And I kind of covered up with my black marker here the normal force, but one of the forces in the y direction is the normal force. There's no component like sine or cosine, it's the full normal force. But with a tilted axis like this, with the gravitational force still being down, I would probably like to think about my gravitational force as made up of these two components here. So part of the gravitational force is in the negative y, and the other part is in the positive x. And for this calculation, I'm interested in the y piece. And so the y piece is not only negative, but it's adjacent to the angle theta. And so because of that, I'm going to put a negative, and then I'll put its magnitude, mg, and then multiply by cosine theta. So these two together are the sum of all the forces. There's only two of them. The full, normal, and a component of the gravitation, and that has to equal to ma, where again, a has to be v squared over r, and towards the center of the circle, which is in the negative direction. All right. Now, one more thought before we kind of circle this question here, is the question said, when does it leave the surface? So, in other words, it's kind of attached to the surface or making contact, and there's a normal force up. And so as long as the normal force is non-zero, it's still in contact. But as it slides over here, as I said, it's going to be going faster and the slope's going to be going steeper. The normal force becomes less and less and less and less and less and less. And eventually it leaves. And when it leaves, the normal force is zero. And beyond that, the only way it could stay on here is if the normal force was negative, pulling it inward. And so if there was some kind of mechanism here, like magnets or something, that help hold it on, it could stay on a little longer. You would just need a normal force in the negative y direction. And again, that's not possible with something that's just resting on it. Something that's resting can only have a positive normal force and not a negative. And so it would separate when the normal force is zero. So I'm going to take advantage of that and say, okay, when the normal force is zero, it leaves the surface, which reduces this down to a negative mg cosine theta minus negative mv squared over r. And even one more step before I put a box around this equation, because there is not only a negative on both sides, there is an m on both sides. So if I cancel that and then move the r over here, I get r times g times cosine theta is equal to v squared. So that I'll put a box. So taking my two pieces of information, this chapter, which is conservation of energy, that's where I got that equation. And then, like I said, going back to what I think is chapter 6, this one here, where we look at the forces, I would have a second piece of information. And let me put those two together. Let me take this equation and substitute it right there for this quantity v squared. So I'll just write the first term, mgr. And then the second term was 1/2 m. And then I got that v squared. So instead of v squared, I'm going to write this one. So rg cosine theta. And then this term would be plus mg r cosine theta. And if you look at this one, you'll see that there is an m in every term I can cancel off. There's also a g in every term I can cancel off. There's also an r in every term that I can cancel off. And so I'm left with 1 on this side. And here is a half a cosine, and here is just 1 cosine. So I can add those together. A half a cosine and a full cosine makes 1.5, or I'll call it 3/2 cosine theta. And then moving the 2 over and also the 3 over, I get cosine theta is 2/3. Taking the inverse operation, or the arc cosine, I can say that the angle would be the arc cosine of 2/3. And that's it. That's what we're asked to prove. We're asked to prove that the angle, when it leaves, is equal to the inverse cosine of 2/3, which we calculated earlier to be 48.2 degrees. All right. Good, tough problem. Got to rely on not just the new stuff, but also the old stuff. Hope that helped.